In the aftermath of recent seismic activity, images from places like Venezuela offer a stark and perplexing sight. Amidst the rubble of what were once bustling urban centers, some buildings stand defiant, seemingly untouched, while mere feet away, others have crumbled into unrecognizable piles of debris. This dramatic contrast isn't random, it's a testament to unseen forces and the profound impact of engineering choices made decades, sometimes centuries, ago. According to disaster analysis reports, such differential damage is a recurring pattern worldwide, challenging our understanding of urban resilience and the hidden vulnerabilities within our built environment. Earthquakes unleash immense energy through seismic waves, vibrating the very ground beneath our feet. But buildings don't simply fall down. Instead, they often fail in specific, predictable ways dictated by their design, materials, and the forces exerted upon them. Structural engineers explain that the ground motion can induce forces far exceeding what a building was designed to withstand, particularly when the building's natural vibrational frequency aligns with the earthquake's pulses. It's a complex interaction, where physics meets architecture, often with devastating consequences. One of the most frequently cited culprits in urban earthquake collapses is a phenomenon known as soft story failure. This engineering term refers to a floor that is significantly more flexible or weaker than the floors above it. Common examples include ground floors with large, open spaces for parking, retail, or lobbies, often lacking the robust shear walls or bracing found on upper residential floors. Experts in seismic design, such as those at the Earthquake Engineering Research Institute, consistently identify soft stories as a critical structural vulnerability that amplifies seismic forces at specific levels. When an earthquake shakes a building with a soft story, the disproportionate flexibility of that ground floor concentrates the movement and stress there. Imagine a stack of books where the bottom book is made of rubber. The entire stack sways, but the rubber book absorbs most of the deformation. According to structural analyses published in journals like Earthquake Spectra, this overstressed soft story can collapse, leading to the catastrophic failure of all floors above it. It's not just a weakness, it's a potential trigger for complete structural disintegration, often trapping occupants. Another terrifying mode of failure is the pancake collapse. This occurs when a floor, unable to support the weight above it, gives way, causing the floor directly above it to fall onto the one below, and so on, in a chain reaction. This creates layers of crushed concrete and twisted rebar, resembling a stack of pancakes. Engineering studies often point to insufficient shear strength, poor reinforcement detailing, or brittle materials as primary causes. Once initiated, a pancake collapse leaves very little survivable void space, a critical factor for rescue efforts. In a pancake collapse, gravity, which normally holds a building together, becomes its deadliest foe. As one floor fails, the dynamic impact of the falling mass above it adds enormous, sudden loads onto the floor below. This cascading effect multiplies the destructive force exponentially. According to analysis by the National Institute of Standards and Technology, NIST, on past earthquake failures, the kinetic energy transferred during a progressive collapse can be far greater than the initial static loads the building was designed to handle, leading to systemic failure even if only one critical element initially gives way. High-rise buildings face a unique challenge: resonance. Every structure has a natural sway frequency, like a pendulum. If an earthquake's seismic waves oscillate at or near this natural frequency, the building can begin to sway with increasing amplitude, much like pushing a child on a swing at the right moment. The accumulated motion can exert immense stress on the structural frame, leading to fatigue and eventual failure. Seismologists and structural engineers emphasize that taller, more flexible buildings have lower natural frequencies, making them particularly susceptible to the longer period waves generated by distant, large earthquakes. The cumulative effect of resonance can be devastating. What begins as minor oscillation can quickly amplify, leading to extreme deformations and stresses in columns, beams, and connections. Reports from the Earthquake Engineering Research Center at UC Berkeley have documented cases where resonance caused non-structural elements like walls and windows to shatter, and in severe cases, led to complete structural failure. It's a battle between the building's inherent stiffness and the relentless rhythm of the seismic event, a battle that the structure cannot always win without specialized design considerations. Perhaps the most baffling aspect of earthquake damage is the sight of some buildings standing strong while identical-looking structures next door collapse entirely. This isn't luck, it's a convergence of multiple factors, often invisible to the casual observer. Experts indicate that these factors range from the underlying geology and soil conditions to the precise details of construction, the quality of materials used, and the adherence to seismic codes that may have evolved over decades. Understanding this paradox is central to improving future urban resilience. One critical, often overlooked factor is the ground itself. The composition of the soil and bedrock beneath a building significantly influences how seismic waves are transmitted and amplified. For instance, soft, loose soils can amplify ground motion much more than dense rock, a phenomenon known as site amplification. Furthermore, in certain conditions, saturated granular soils can undergo liquefaction, temporarily losing their strength and causing buildings to sink or tilt. Geotechnical engineers consistently stress that a thorough understanding of site-specific geology is paramount for effective seismic design. The age of a building and the seismic codes in effect at its time of construction are also major determinants of its resilience. Modern building codes, like those developed by the International Building Code, IBC, and local ordinances, incorporate decades of lessons learned from past disasters. Older structures, built before these codes were updated or even existed, often lack critical reinforcement, ductility, and design features necessary to withstand significant seismic events. Reports from groups like the American Society of Civil Engineers regularly highlight the vast performance gap between legacy and contemporary construction. The choice and quality of construction materials play a pivotal role. Reinforced concrete, for example, is ubiquitous, but its performance depends heavily on the amount and proper placement of steel rebar, as well as the concrete's strength and mixture. Materials with inherent ductility, like steel, can bend and deform significantly without fracturing, absorbing seismic energy. Brittle materials, such as unreinforced masonry, offer little give and are prone to sudden, catastrophic failure. Material science research continuously pushes for stronger, more flexible composites to enhance earthquake resistance. Modern earthquake engineering has made significant strides in designing resilient structures. Innovations like base isolation systems, which essentially decouple the building from the ground using flexible bearings, allow the ground to move beneath the structure without transferring its full force. Tuned mass dampers, large pendulums or weights installed in high-rises, absorb and counteract sway from resonance. These sophisticated technologies, as detailed by leading engineering firms, represent a proactive approach to mitigating seismic risk, moving beyond mere survival to ensuring operational continuity. For existing structures, particularly those identified as vulnerable, seismic retrofitting offers a lifeline. This process involves strengthening a building's weak points through various techniques, from adding shear walls and bracing to installing external steel frames or carbon fiber wraps. While costly and often disruptive, retrofitting projects, guided by civil engineering firms, are crucial for protecting populations in seismically active regions. Many cities, recognizing the inherent dangers of older building stock, have implemented mandatory retrofitting programs to upgrade safety standards over time. Despite these advancements, significant challenges persist. The sheer number of existing unreinforced or poorly designed buildings worldwide presents an enormous, often insurmountable, retrofitting task. Economic constraints often delay or prevent necessary upgrades, particularly in developing nations. Furthermore, even with the best engineering, predicting the exact nature and intensity of future earthquakes remains elusive. As highlighted by the Global Earthquake Model Foundation, the variability of seismic events means no design can offer 100% guaranteed immunity, making continuous research and adaptation essential. Beyond scientific principles, human factors critically influence earthquake performance. Shortcuts in construction, inadequate oversight, and corruption can undermine even the most robust designs. The integrity of building materials, the precision of their assembly, and strict adherence to codes are all essential. Reports from post-disaster investigations frequently reveal instances where a failure to follow specifications directly contributed to catastrophic collapse. It underscores that engineering isn't just about calculations, it's about ethical practice and rigorous implementation at every stage of construction. Modern earthquake engineering is moving beyond simply preventing collapse. The new frontier is functional recovery, designing buildings that, after a major earthquake, can be reoccupied and operational almost immediately. This requires not only structural integrity but also protection for non-structural elements like plumbing, electrical systems, and sensitive equipment. The American Society of Civil Engineers' latest performance objectives aim for minimal downtime, recognizing that the economic and social disruption from prolonged building closures can be as devastating as the initial damage. The lessons learned from past disasters, including those witnessed in places like Venezuela, continually reshape our understanding of seismic safety. From sophisticated analytical models to innovative materials and construction techniques, the field of earthquake engineering is in constant evolution. While the Earth's movements remain unpredictable, our ability to design and build structures that can withstand its fury is steadily advancing. It's a testament to human ingenuity, a relentless pursuit of safety that strives to turn every collapse into a lesson, and every lesson into a stronger, more resilient future for our cities. The devastating scenes from earthquake zones worldwide underscore a critical truth: buildings don't just fail, they reveal the choices and oversights of their creators. Our investigative journey into soft story failures, pancake collapses, and resonance amplification has shown that understanding these engineering vulnerabilities is the first step towards preventing future tragedies. The quest for true seismic resilience is an ongoing endeavor, demanding vigilance, investment, and a steadfast commitment to building not just for today, but for the unpredictable forces of tomorrow. The safety of our communities depends on it.